Sorry, something. Yes, let me start my talk. I'm going to talk about using RDMA and malleability for application level checkpointing in HPC systems. So this is the overview of today's talk, where I start with the need for dynamism in checkpointing, followed by introducing iCheck to you, and specifically invasive checkpointing concepts and what does the word invasive mean in this context, and talk about our infrastructure, and followed by the dynamism in our checkpointing system, and we'll conclude with results and outlook into the future. So let me begin. So there are plenty of techniques for fault tolerance in the field of computing, and in HPC also it's the same. So it's the same concept. Like you have system level checkpointing, application level checkpointing, then process recovery, data recovery. There are plenty of fault tolerance techniques, and we focus on application level checkpointing restart, which is widely used in high performance computing simulation applications. So the idea here is the application developer write the data that is needed to successfully recover the application if any failure happens. So basically, you specify what all data needs to be checkpointing. That is called application level checkpoint restart. And there are an alternative ways to have system level checkpoint restart where the entire state of the system is checkpointed. So we focus on application level checkpoint restart in this work. And when you look into the HPC, you always see that HPC has a static view of resources. That means if an application is started with n nodes, the HPC expect that the application will use n nodes throughout its execution and ends with n nodes. But often the application characteristics doesn't record this n nodes the whole time. You can start with a lesser number of nodes, and then at some point you need more nodes, you perform more computation, so you need more resources, and then after that you can give back the resources and continue the execution. So this is kind of the dynamic view, characteristics of the applications, which is frequent in cloud computing domain, but which is not a common scenario in HPC, but that is changing. So a lot of researchers are actively looking into creating a malleable system software as well as programming models and applications in HPC. So towards that extent, the checkpointing system should also be able to provide this dynamic capability or support dynamic HPC applications. So the obvious advantages with dynamism in checkpoint is improving the application performance. If you can add resources or add checkpointing resources on the run, then definitely your application will benefit from that. And then the next improvement can be in system utilization. So if you have a global view of checkpointing happening in your HPC system, then you can coordinate or orchestrate the checkpoint retrieval and then effectively utilize the bandwidth. So these are some of the advantages offered by dynamism in checkpointing. So we propose iCheck as a kind of a system where rather than simply providing a one-to-one checkpoint mapping, like application write the checkpoint and then system writes back in the parallel file system or store the checkpoint, we view the checkpointing process as a checkpoint and data management process. That means you orchestrate the checkpoint retrieval, you perform optimization, and later you can write in the parallel file system or not based on the characteristics of the system. So for all these to work perfectly, your checkpoint system should be able to perform efficient checkpoint retrieval and checkpoint write. For that, we use RDMA. So our system will remotely read the checkpoint from application and then stores it and process it and write it. So we use RDMA under the hood for all this checkpoint retrieval and checkpoint management process. Towards that end, we present our checkpoint system called iCheck or invasive checkpoint system. It's a fully adaptive invasive checkpoint management system. So what does the word invasive mean in context? So invasive comes from the Invasive Computing Project, which is a German research foundation funded project, DFG funded project called Invasive Computing or Invasive, which focus on creating dynamic resource management on massively parallel multi-chip processors. So here we have the concept of resource-aware applications that invade the field cores and then perform some computation on it, infect or retrieve from the resources. And towards that extent, we have this whole tech stack that spans from hardware, operating system, language, compilers, tools, and applications. So we have the whole tech stack created as part of this project. But from the side of Technical University of Munich, we focus on bringing the concepts of resource-aware applications like invading, infecting, and rotating into the HPC domain. So HPC has the static view of resources, but we want to take this invade, infect, and retreat concepts into HPC, into the resource management, and into the programming models, into the application. So we focus on that. So iCheck, or our checkpoint system, is created as part of this invasive project and supports invasive or malleable applications developed using invasive HPC infrastructure. So there are like terms: invasive, malleable, dynamic, adaptive. Unfortunately, the word is not standardized. The whole this plethora of words means the same thing. It's like resource aware. It's not rigid or static. If your application is malleable or dynamic or adaptive or invasive, that means it can change the number of resources, or it can change the characteristics on the fly. So basically, in the malleable scenario, iCheck supports applications created using this invasive infrastructure. iCheck also supports standard MPI applications or non-MPI applications and provide checkpoint service accordingly. So we have invasive infrastructure that caters around system level, application level, and service level. And I will introduce you the system level, and then later I will introduce you to our checkpoint management system called iCheck. So first, we have this invasive infrastructure, consists of invasive resource manager, which is an extension of Slurm with dynamic resource management capabilities. And then we have invasive message passing interface, or IMPI. It's an extension of MPICH with 4 new operations for dynamic process. They are MPI init adapt, probe adapt, com adapt, begin, com adapt, commit. So if you are into MPI, you can see that we have now converted with MPIX init adapt or MPIX probe adapt, because this was created a while back. That's why in the latest release, we will be changing the name to MPIX init adapt to the standard. So sorry for that. So how does this invasive resource manager work? So in a nutshell, you can see the figure here on the right side. There's an invasive batch scheduler that separates the jobs based on the characteristics. So if your application is a static one, then it's part of a rigid job queue. If your application can change on the fly, then it's part of elastic job queue. And our invasive batch scheduler will sort that and schedule the jobs based on some scheduling policies we have implemented. An invasive runtime scheduler that during each scheduler pass looks into the running applications, and based on some constraints or power constraints or performance constraints, decide which applications should get more resources, or from which applications we should take back the resources. So basically, IRS, or invasive runtime scheduler, decides about the resource reconfigure, and the application sees that, and the application adapt to that. So that is how this invasive resource manager works. And with respect to iCheck, we have an iCheck aware invasive runtime scheduler, which can give these nodes or compute nodes to our checkpoint system if needed. So I will explain in detail in the coming slides. So this is the outlook of IRM. And then we move to IMPI, or invasive MPI. Here as I mentioned, we have created 4 new functions for that. And MPI init adapt is to replace MPI init. So if you call MPI init adapt, then it informs the resource manager that our application is a dynamic one or a rigid one. And then com adapt begin and com adapt commit is used to create the adaptation window in which application can redistribute the data or perform data transfer. And then there is MPI probe adapt, which can be used by the application to see whether there are any resource changes triggered by invasive resource manager. Okay, so how all these things work in an application level. You can see this is a simple invasive MPI application, pseudocode, and our functions are marked with red color. So this is the typical view of a simple application, and you can see there are multiple control flows. Let me move on to the basic control flow. So when an application is launched, it has this view. So initially the application calls this MPI init adapt, and then so this is to replace the MPI init call. So when you call MPI init adapt, our resource manager MPI sets a flag in my type. So the application can then use that flag to check that whether the application is part of an initial process or application launch, or this process was created as part of a resource expansion triggered by the resource manager. So if it's an initial process, then everything is easy. So you can directly start your execution of the application. So typically in simulation application, we have a large iterative loop where you perform some mathematical operation or you perform some computation, and this is done in a loop for example, time steps or something. So you perform this iteratively. So this is how the standard flow of a typical MPA application. But since it's an invasive application, it occasionally also checks for any resource changes happening. So it checks using this MPA probe adapt code. But with some heuristics, our invasive resource manager sees that new application needs to be launched, then it can launch new process. So decides that new process can be created for this particular application, then our resource manager launches this process. And when they are launched, they call this MPA init adapt. And with this flag, they can see that, okay, I'm not part of initial process, but rather I'm part of newly added set of process, or I'm a joining process. So for that process, I should immediately start the adaptation window. Why? Because to perform some meaningful computation for a newly added process, it needs to have some information like what is the current state of the application, or where should I start from where should I start my execution? What all of the data should I work on? So it needs information or metadata about the current state of the application. So it immediately called comma begin. So all the newly joining process can call this comma begin, and then meanwhile the initial set of process that's in the iterative loop can call probe adapt, and then it sees that there is a resource change is happening, or there has been some resource changes. So then it can call comma begin, or it can jump into the adaptation window. Now all the joining process and existing process are there in the adaptation window, and then they can redistribute the data to start the computation. So how does the checkpointing and RDMA comes into this aspect? So here, since I mentioned the in application level checkpointing, the application developer writes the checkpoint that needs to restart the application in case of a failure. So it has the necessary information that is needed for the execution of the application. So if we can annotate some partitioning strategy, partitioning information like whether the data should be distributed in block or cyclic. So if you can add some extra information, you can revision your checkpointing system as a data redistribution mechanism. So in that sense, iCheck provides support to malleable application. And after that, it can call commit and then finish the resource expansion. So, and then all process can start working together. So this is the whole idea of invasive infrastructure. We have a resource manager that can analyze the current system view, and then decides which application should get resources or which application should give back the resources. And then these applications that are able to adapt according to the resource changes triggered by the resource manager. So this is the whole invasive infrastructure. And how does the iCheck comes into play here? So let me start by introducing iCheck to you. iCheck is an invasive RDMA-based multi-level application level checkpointing system. So here the multi-level means iCheck stores the checkpoint in iCheck memory as well as in parallel file system. Okay, and iCheck is deployed in dedicated nodes in an HPC system or HPC cluster. So iCheck has a core component and library, and if you look into the figure in the right side, you can see iCheck system is running on a resource allocation. You can also see the legend here. It's running on resource allocation, and there are multiple applications that is running on compute nodes on different allocation. And then you can see there is an iCheck controller that is running on a compute node in the iCheck system, and it has the global view of the system, while the manager has the local view of each node. And the agents, there can be multiple instances of agents in iCheck node, which is dedicated, which is responsible for reading checkpoint from the application. And as seen from the figure, multiple applications can be connected to our iCheck system. And iCheck system uses RDMA to read the checkpoint, read and write the checkpoint. So with this limited information itself, we can see the enormous potential offered by dynamism. So since the system has a global view of checkpointing happening, it can orchestrate the checkpoint read and write in such a way that the bandwidth, the whole network bandwidth is efficiently utilized. So, and by using RDMA, you can avoid the unnecessary interaction with the CPU or wasting the CPU time of the application. So this potential offered by dynamism is enormous in a checkpointing system using RDMA. So in the regarding the whole workflow, initially application registers with the controller, and then controller assigns the agents and iCheck nodes. So this requires some careful planning, because here you can see applications are connected, multiple applications are connected, and the controller can place agents associated with application in any manager nodes. So there are agent placement algorithm and node selection algorithm to decide the number of agents and to decide which manager should have which agent. So this is very important because this can definitely affect or improve the performance of the application, which I will show in my evaluation section. And after that, manager launches the agents and agents connect with the application. During this time, the RDMA configuration is performed, like the key exchange is performed. And then application will commit and then continue the execution. Meanwhile, the agent can retrieve the checkpoint using RDMA without the involvement of application. Okay, so how does the RDMA works here? So the idea here is application register its memory regions with the agents. So both memory regions of agents are registered, like agents and application is registered such that the agent can access the application and application can access the agent. So we use a sleep fabric for that. And there are multiple techniques in iCheck for that. So one technique is where each MBA process registers a particular memory pool to store the checkpoint with the agents, corresponding agents, and then agents can retrieve it remotely. And since this registration is kind of overhead, creates overhead, there's also RDMA plus shared memory implementation where we have one process that uses shared memory, create the shared memory, and then this shared memory is registered with our agent as the memory region in Leaf Fabric, and then our iCheck agent can read the checkpoint using RDMA from this particular single process, and all the other processes in the compute node use the shared memory to write the checkpoint. So this can reduce the number of key registrations and key transfers. So basically, once the whole thing is configured, we perform the key exchange, and the memory registration is done. Then you can do the checkpoint transfer. So there are two techniques provided by iCheck for that, pull and push techniques. In push techniques, application can write directly into the memory of agents using RDMA, while in the pull technique, agents can read directly from the application memory the checkpoints. And then the agents can write the data into parallel file system. Okay, so how does the dynamism in iCheck plays around? So it can have a system level dynamism in iCheck where iCheck can increase the number of nodes and change the agent behavior. And in the application level dynamism, iCheck can increase the number of agents and also provide data distribution support. And the RDMA comes around, or RDMA plays significance in this application level dynamism aspect. So in the system level dynamism, you can see we have an iCheck aware scheduler that can request for more nodes, and then our invasive resource manager, dynamic version of Slum, can give more resources to a checkpointing system or more compute nodes to the checkpoint system for writing checkpoint based on the current system statistics. And in the system level aspect, like as I mentioned, the checkpoint is retrieved by agent, and agents are like the lowest level that reads or writes the checkpoint from application. And RDMA and data management is the basic functionality of the agent. But other than that, agent can do a lot more than checkpoint retrieval. Based on the application, it can either perform like data compression if the checkpoint size is larger, or if the application is a malleable one, it can perform data distribution. It's a kind of pluggable services, and agents can, and these pluggable services can be added to agents on the fly. So from the application level dynamism, we have this basic API for iCheck, like iCheck init is to say that to connect with the controller, and the iCheck add can be used to add the data structures to be checkpointed, and commit will ask the agent to read the checkpoint, and restart and restore is used for during the application crash or failure and restart, and then finalize. And there's also asynchronous functionality to read the checkpoints. And we also provide iCheck probe agent support that can be used to change the number of agents dynamically or on the fly, such that the application performance can be improved. And during this agent change also, we need to reconfigure RDMA for all the process. So this is kind of the overhead associated with the agent change. And as I mentioned, iCheck, so the checkpoint system can be used as a data redistribution mechanism in case of malleable applications. And we provide extra API called add adapt to add the data structures that needs to be redistributed during the resource adaptation. And then when there is a resource adaptation happening, then you can use the redistribute API. So these are specific to iCheck, but the general idea with this thing, or what we propose with iCheck, is that rather than seeing checkpointing system as purely a one-to-one mapping to write the data in the parallel file system, we can do more like data distribution and then or optimizing like compression, and all those things can be done under the hood if you look the checkpoint or consider the checkpoint system as a whole system that has data and checkpoint management capabilities. And from the evaluation side, we perform some basic tests on SuperMOOC NG. It's a supercomputer at LRC, Germany, and we perform. Sorry.
No.
Okay. So we performed the evaluation on 16 nodes, and 12 nodes were dedicated for applications and 4 nodes for iCheck. And for our simple evaluation, we use LS1 Martin, which is the molecular dynamic simulation application. It's the largest molecular dynamic simulation application, and then Luillage and heat simulation, as well as synthetic application that checkpoints 2.3 gigabyte per second of data. And some scenarios were compared, where we compared the iCheck performance with in-house MPIO in LS1 Martin, and also we compare the performance of iCheck with MPIO and SCR in a synthetic application. SCR, or scalable checkpoint restart, is most popular checkpointing application in HPC, I would say. And then we also studied the effect of dynamic agents on a 2D heat simulation application, as well as effect of different agent placement strategies using multiple synthetic applications. So we also performed a lot of other tests, but for saving time, we only put some results here. So this is the basic evaluation of iCheck versus MPIO, and you can see that the time for checkpointing in iCheck is much less, and it performs up to 5,000 times faster checkpointing than MPIO, because the reason is obvious. iCheck uses RDMA, and it is faster than writing the parallel file system, and the size in the data size or checkpoint size in LS1 Martin or simulation, generally this molecular dynamics application is few, or say in range of few megabytes. So MPIO does not perform well in that sense. And so by using the RDMA, iCheck can fastly retrieve the checkpoint for a small size of checkpoint data. So that's why we get around 5,000 times performance. But we also compared with scalable checkpoint restart, and you can see that iCheck performs up to 57 times faster than SCR, and in the worst case, like using one single agent. So this is like really worst case, and you get faster performance than SCR. This performance is due to the effect of using RDMA under the hood, like agents are retrieving the data directly without the CPU involvement. And here it's also blocking implementation. So if you use a non-blocking implementation of iCheck, where the application can then resume the execution, then you will have much more better results. So, and this is kind of effect of dynamic agents on a 2D heat simulation application. So our iCheck controller increased the number of agents on the fly, and you can see that the checkpoint time was kind of halved, and after some point it's saturated. So it doesn't always get beneficial to add more agents or do more resources or give more resources. So there has to be some heuristics that need to model the performance characteristics of the applications to efficiently utilize the bandwidth, available bandwidth. And then this result shows the effect of different agent placement strategies in a synthetic application. So the whole idea here is we ran multiple synthetic applications together, and we recorded the available bandwidth for checkpoint transfer, or the obtained bandwidth for checkpoint transfer in a particular synthetic application. So for that, we place the agents for checkpoint retrieval for these applications in a single node called stacking strategy, bandwidth based on the network bandwidth available in checkpoint nodes, and then based on the checkpoint interval happening on a particular node. So, and you can see that when we optimally place the agents, the fluctuation in bandwidth, or the aggregate bandwidth available to transfer the data is really good in bandwidth strategy. That means you get around like 9 gigabyte per second to 12 gigabyte per second if you place these agents optimally. So that's why I mentioned it's really essential to orchestrate this checkpoint retrieval and place agent and manager selection, because this can really improve the overall performance of the application. And from the challenges side, so we are just providing this prototype system where you can see the performance improvement. So since the prototype system usually provide a data redistribution capability for block or cyclic data redistribution, but in reality, you have like complex data types graph, so that needs to have its own, or data partitioning libraries are there for large-scale simulation applications, so it does not support it, so we have to provide that. And then agent placement and efficient resource utilization is also tricky because it's based on application characteristics and underlying system. And also, since we provide or vision this checkpoint library as a checkpoint management system, multiple applications checkpoint data is stored in a single system, and this might affect the privacy requirement of some application that is running in this supercomputing center. So that's also a challenge. But when we look into the future, we have like a lot of optimization potential because we provide these pluggable services, so we can change the API into the parallel file system without the involvement of application developer. Or in case of malleable applications, we can use the checkpointing as a data and resource management, so it can cater to the needs of malleable applications as well as non-malleable applications. And later, we are also working on deploying iCheck in the cloud. Since most use cases are moving on to HPC on cloud, we are actively working on implementing or deploying iCheck on the cloud. And now our policies for checkpoint management were based on performance of improving the performance application. So this can be changed. For example, power aware scheduling can be implemented. So we have our power corridor management technique where we have created a batch scheduler that can maintain overall system or maintain the total power usage of a system in an upper and lower limit based on some constraints by reconfiguring the running application. So we have that batch scheduler for power management. We can integrate it and make sure that the checkpoint system works within a certain power range. So policies for checkpoint management can be added easily with such a design. And currently we only support compute nodes that doesn't have GPU, so we need to also provide support for GPUs and FPGA. So this is kind of the overview about our iCheck system, and the core performance improvement iCheck is due to the impact of RDMA under the hood, and we are using libfabric version 1.9 for our implementation. And we have tested our iCheck implementation in SuperMOOC NG, and we'll be testing that on one machine in EPCC at Edinburgh in the coming future also, to see how the libfabric how the performance can be improved or how the performance varies. So by this I summarize my talk. And if you have any questions, like you can ask now, or if you need to know more about our InVasic project, you can visit the QR code in the left side. And if you need to know the work happening in our department, Chair of Computer Architecture and Parallel Systems, you can use the right QR code. Okay, thank you.
Cool, thank you. We have a couple of questions, and then I have a couple of things I'd like to ask as well. First question from Sean. Would iCheck be able to leverage the RDMA operations with an on-the-fly data compression option?
Yes, it should be, yeah. We haven't tried that. We only tried using, after reading the checkpoint, we added our checkpoint plugin, and then we compress checkpoint and write it. So we haven't tried the on-the-fly, but it should be possible.
I don't know, Sean, if that answered your question appropriately. We also had a question from Benson. IO nodes are usually shared. Does this give variability in checkpointing speed?
So here we are using like the compute nodes for the checkpoint transfer. Basically, like iCheck system is also running on the compute nodes of the supercomputing system. So there is like definitely the variability, because if you are running like Linpack or a high application that uses high IO or require high usage of IO, then the performance of the checkpointing will vary. That's what we showed with this last graph, where you can see that if you place the agents, or if there are checkpointing happening, like frequent checkpointing happening and the bandwidth is saturated, then you get like bad performance. So you have to care for that also.
Cool, thank you. Could you please go back to slide 35?
Okay.
Could you explain, you kind of flew through this a bit fast. Could you go over this again? I didn't quite understand the graph on the right. Could you explain that again?
Okay, this
your
graph.
ranges there. Yeah, your ranges.
Okay, so this is the time consumed for checkpointing. So we ran LS1 Martin for it's a simulation application for around half an hour, and when you use MPAO, you spend around like 100 seconds for only for checkpointing. So this much time is used for checkpointing, but when you use RDMA and you run the application for around the same 30 minutes, you can see that it only uses 0.5 seconds for a whole checkpoint transfer process.
Okay. And then slide 39, please.
Okay.
Can you expand on checkpoint management when you were talking about some of the parameters and characteristics here?
Okay, so you mean the agent placement, or?
Well, yeah, I think again you flew through it kind of fast. But as I said, if I recall properly, you were talking about there were certain options or parameters that you could put in here, and I was wondering if
Yes. So so the idea here is like you can place agents with different philosophies. Like, okay, you have different iCheck nodes that can be, and your controller knows how much memory is available in each iCheck node, or how frequently some applications are checkpointing to this particular iCheck node. So this controller can make some decisions like, okay, since this application is checkpointing frequently, you need to have agents placed on multiple iCheck nodes. And this, say, another application B, checkpoints only like rarely, but it checkpoints large amount of data, then dedicate this particular node only for this application. So you can tune this kind of information, like how to place these agents, or or where to place the agent. So that information can be, that decision can be made by the controller to optimize this checkpoint retrieval or optimize the whole system utilization.
Thank you. I think that clarifies that. Okay, does we have anyone else have questions? We are running a little ahead of schedule. Let's see. Next, we'll have. I think what we'll do is we'll probably take just a couple of minutes pause here just to try to catch up with schedules. Just.